As usual, we'll begin this lesson with a fairly simple definition, this one adapted from Wikipedia. An arithmetic sequence is a sequence in which successive terms are separated by a common difference. And just as a note, because I know some people are already thinking it, yes, it's pronounced arithmetic when talking about sequences. Arithmetic is a noun that refers broadly to number theory. Arithmetic is an adjective that describes the nature of something. Here, a sequence. Anyway, getting back to the lesson, there are typically two ways to write an arithmetic sequence. One way is implicitly, a form in which you need to know the value of a previous term to generate a future term, so this has a tendency to look recursive by nature. So here, for example, we have a sequence defined in which the first term is a 4, and the common difference is a 5. Reading that second line under implicit form, a sub n is equal to a sub n minus 1 plus 5, we see a sub n representing both the sequence definition and the way to generate the nth term. And that is equal to a sub n minus 1, which is a common way to say the previous term. Plus 5 indicates our common difference, because as we go from one term to the next, the values in this example are going to differ by 5 each time. The other way we could have written this example sequence is explicitly, or in explicit form, in which we have a general formula that can describe the nth term directly. Explicit form really wants 2 or 3 things. One is the first term of the sequence you're trying to work with, a sub 1. Another is the common difference. And lastly, if instead of generalizing you actually want a specific term, you're going to need a value for n. But when we generalize like this to come up with the formula, we leave this as n to say, hey, we can replace this whenever we want. Now, I'm going to argue that even if you've never seen sequences before, you've probably memorized this form already. We have a value that depends on a common rate of change being applied to a variable number of terms, with an initial value being added at the end. I wonder what this looks like. In any case, once we have the general explicit form set up, it becomes a simple substitution. And as the calculations carry themselves out, we really get a glimpse at something that resembles slope-intercept form of a line. We have to be very careful, however, because an arithmetic sequence is not a line. Recall that our input values for n here are only the natural numbers, so the sequence is discrete, not continuous like a line would be. Let's get right into this with an example of how a sequence might be set up. Here we're asked to identify the next 4 terms in the sequence defined by a sub 1, or the first term, being 23, and the nth term being equal to the previous term minus 7. So the first thing I'm going to do is draw out a few spaces to hold the terms of our sequence. This is a quick and handy way to keep track of some of the values instead of just listing them arbitrarily. Then, we're going to fill in these spaces with their indices, so that term 1 goes in our first spot, term 2 goes in our second spot, and so on. This allows us to insert 23 as a sub 1. Reading the second line in the sequence definition now, we see that there is a common difference of negative 7. What this means to us is that each new term is going to look at the previous term and subtract 7 from it. Once we establish this pattern, it becomes a simple calculation to identify the next 4 terms. Now we'll look at a situation when it's a little less practical to rely on the implicit definition. Here, we're asked to use the same sequence, but determine the 2020th term. Hopefully it's obvious that generating one term after another for over 2,000 steps isn't really ideal. Let's try to make a few key observations and figure out a way to do this more efficiently. Firstly, let's again remind ourselves where we're starting. Our initial term here is 23. And then from here I'm going to make some room so we can start listing out the terms again, but this time in a more tabular form so we might be able to get a clearer picture of what's happening. We'll write in the first term as we know it, and then we recall from the previous slide that each successive term had us subtracting 7 from the value we already had. Of course, I did just say that this would be a less than ideal method of generating the 2020th term, so let's look at what this is really telling us. When n is 1, our term is just 23. We haven't had any need to introduce our common difference, so the negative 7 applies 0 times. As we start to increase our index, looking at subsequent terms, we see a really convenient pattern emerging. For example, for us to have reached the 4th term, here where n equals 4, we had to start with our first term, 23, and then add the common difference only 3 times, right? We don't introduce the negative 7 on our first term, but to go 3 more terms, we have to introduce that difference 3 times. And if we look further on at the nth term, representing anywhere within this sequence, we construct ourselves the formula from the definition page, which is that the nth term is given by our first term plus the common difference being applied n-1 times. This general form now can be used to evaluate the 2020th term by substituting 2020 in for n and calculating the result. Just please note that this was not an exhaustive list of ways to use, interpret, or evaluate arithmetic sequences. And as always, please leave me any questions, comments, or concerns.